I'm detecting DNA. One is I want to give you an of evanescent wave sensing, and the idea over here is that when you pass light through a waveguide trapped like in a fiber or in a planar waveguide film, you trap light. Light is bouncing back and forth, propagating. So these are called optical waveguides for chemists. Either fiber where you pass light and light is trapped and comes at the end, or you have a film, you trap light and it moves around at the end. But on the surface of that, still the light's electric field goes out. And if you deposit something on the surface, let's say fluorescent organic molecule, if the energies match the frequency, it will excite fluorescence on the surface, okay? Or it can convert, the film has nonlinear effect, it can do harmonic generation, you know, or it can change the condition that the light from inside leaks out when something is deposited. So this evanescent wave is the wave that protrudes from the guiding film or guiding fiber a little bit, and this extends only to like maybe maximum of 100 nanometers, okay, from the surface. It doesn't go all the way out because it's trapped field. So you use that wave to sense, and so you can make a fiber sensor like this. Fiber generally that you use like in optical telecommunication, where the telephone lines are through using light. In the fiber, you have a core, and core is a material that has high refractive index. By the way, this is another area there is a lot of interest using plastic fiber, polymer fiber, rather than glass fiber, which is being used now. There are certain advantages. So it's used over here. But anyway, so you normally have a core that has high refractive index, and it is covered with a sheet of something like electrical conductor. You have a conducting wire, then you have insulating layer covering it. Similarly, over here, you have a layer that's called cladding layer of different material. So you can strip that cladding layer so that this core waveguide fiber is exposed on the surface. And then you can deposit over here, let's see, an antibody, okay? And then you can actually have, okay, and you can have actually your sample that you sent in there, and the sample actually is, let's see over here, in your sample disease cells, so on, and it has antibody that can actually attach to it, antigen that can attach to it, and then you can have another antibody that has a fluorescent probe, okay, complementary to this. So remember, the antigen connects to antibody, and then the other side, again it can connect. This is called a sandwich arrangement. And then the light is going through here. The light can interact through evanescent wave and generate fluorescence. And once you detect fluorescence, you say, well, okay, this antigen must be there. If it is not there, it cannot grab the fluorescent label antibody. Okay, so that's the principle you use. You can use the fiber geometry by fluorescence scenting